Let's see some final results about convergence and then open up a new chapter. The first one is a corollary of, let me see, of a theorem, of the last theorem that we saw, and it's called Skorohod representation. It says the following: if a sequence xn converges in distribution to x, well, a sequence xn converges in distribution to x if and only if there exist random variables y1, yn, on some probability space, let's call it like this, such that yn converges in distribution to y, no, to x. To xn for any n, and y converges in distribution to x. And moreover, yn converges almost surely to y. So we have a sequence that converges in distribution. There exist some random variables on some probability space which converge in distribution to the same original sequence of random variables. The limit of the two sequences, well, the limit of the second sequence converges in distribution to the limit of the first. But the important thing is that the second sequence converges almost surely to some random variable. If xn converges in distribution to x, the following are equivalent. Xn is uniformly integrable. Let's put it like this, ui. Xn and x are integrable, and the expectation of xn in absolute value converges to the expectation of x in absolute value. And now let's talk about Fourier transform. Let Fn be a sequence of Fourier transforms. Of the following measures mu n for any n such that Fn of r is the integral over r of exponential minus, well, no, it's not with a minus here, irx mu n dx. For r in the real numbers, Now, mu n is weakly convergent if and only if the limit of the Fourier transforms converges to some Fourier transform f of r. For any real number r, and f continues at 0. Moreover, f is the probability measure of a probability measure mu on R, which is the weak limb of the sequence mu n. So we have that if the Fourier transforms of a sequence of measures converges, then the sequence of measures is weakly convergent, I guess. And one consequence of this is that xn converges in distribution to x if and only if the limit of the Fourier transform of, well, the limit of the characteristic function of xn is the characteristic function of some random variable x. For r in the real numbers, okay, so we saw basically all the results related to convergence, and now we want to see something more about the limiting random variable x, because up to now we just talked about the sequence itself and where it leads, but we want to understand better what is the thing that it leads to, in some sense. So here we have an important theorem, which is the law of large numbers. And this is for finite mean and variance. So consider a sequence of pairwise independent random variables. Pairwise independent, with common mean and variance. The mean is, let's call it A, and the variance B. Then, what can we say? The random variable xn bar is such that, well, xn bar is the average. This is the sum from 1 to n of xi over n. This thing converges in L2 to some measure this converges to the mean, the common mean of the random variables. Then we have that xn bar converges in probability to the mean, and it also converges in L2, well, but this is, I don't know, almost surely to A. So in some sense this implies this, and it implies also this, I think. So let's try to state it again. Theorem, we have a sequence pairwise independent with common mean and variance. Then xn bar, which is the mean of the variables composing the sequence, converges in L2 to the common mean. It converges in probability, and it converges almost surely as well. Proof. Let Sn be n times the sample mean. I call it sample mean, but it's the mean of the random variables here. And the expectation of Sn is n times a y here we sum the xn bar since the expectation of each random variable is a. When we sum them, we get n times a. Okay, makes sense. Now, the variance of Sn is nb because pairwise independence, because of pairwise independence. So then the expectation of xn is a, and why is it important here? I will just omit it. Then the variance of xn bar is b over 2 to the n. No, b over n. Which means that the expectation of the square of the absolute value xn bar minus a is the variance of xn bar, and this thing goes to 0 as n goes to infinity. Hence, xn converges in L2 to a, this comes from Markov. And it was already proved, it says. Maybe I remember the result. I mean, I remember I saw it, but I don't remember it explicitly. It was just a one line involving an inequality. Let's skip it. Now assume xn positive. And define n to be the sequence nk with k in the positive natural numbers such that nk is k squared. Now by Chebyshev, we have that the probability that xn bar differs from a for a value larger than epsilon, this is bounded by the variance of xn bar over epsilon squared. And this is actually b. And here we have also k squared y. In any case, rearranging and summing, we have epsilon squared, the probability, blah blah blah, but this thing, why do we have the sum here? Okay. Let me write it in this way. Epsilon squared is a constant, we can take it out of the sum. This thing is finite for any epsilon greater than 0, why? Because as k goes to infinity, this thing becomes 0. Now, applying the Borel-Cantelli lemma, we have that xn bar converges to A almost surely along n. And call omega 0 the almost sure set on which converges, or in which convergence takes place, and for any omega in omega 0, we apply the following lemma that we have already proven for any, well, xn positive, x and bar being the sum of xi over n equal nk, so that we have asymptotic linearity. Oh, this was the result from real sequences. This is 0. No, this is a constant which is positive. And now if x and bar converges along n to x, then x over r is bounded by delimif, and this is another result that we saw. X and bar, which is in turn bounded above by delim sup, and this is less than x times r. Now note that k plus 1 squared over k squared goes to 1 as k grows. Hence, for any point in the almost sure set in which convergence happens, we have this. The key is here, this goes to 1, so this becomes 1, this becomes 1, and so here we have A and A. But this means that the limit Sn grows of xn bar is A, and this simply means well, this for any omega in omega 0, which is almost sure convergence. So, to prove the third point, that the mean of the random variables converges to some value a, which is the common mean of the random variables, we used these two results from real analysis. And we applied the Borel-Cantelli lemma. How did we apply it? It's not very clear to me. How did we apply the Borel-Cantelli lemma? And we can relax the hypothesis for random variables having infinite mean. Xn IAD with infinite mean and consider a further random variable x distributed as xi, then the mean of the random variables converges to, well, diverges almost surely. Fix a real number b positive and let yn be xn times an xn maximum b or minimum b, I never remember the symbol. Let yn bar be the average of the yi's, and note that the expectation of yn is the expectation of x minimum b. I will call it minimum even if I'm not sure if it's the minimum or the maximum. Now, by a previous theorem, what do we have? We have that yn bar converges to the expectation of x minimum b almost surely. And now xn bar, no, xn is greater than yn for any n, which means that the limit of xn bar is greater this should be true for any b and means that the expectation of x minimum b as b grows goes to the expectation of x, which is infinity. Okay. This is a quite challenging part. And now we see the more general version of the law of large numbers. I don't have the proof that, I think. In any case, let's state it. Again, consider xn pairwise independent random variables with the same distribution as x. If the expectation of x exists, infinite values are admitted, then the expectation of xn then xn, why xn and not the expectation of xn? I think it should be that. Okay, no. Xn bar converges to the expectation of x almost surely. Basically, the law of large numbers is a result related to the mean. To the convergence of the mean of a sequence. Okay, and let's take a look at more inequalities. Consider xn IID such that the expectation of xi is 0. Then Chebyshev becomes epsilon squared the probability that xn is larger than epsilon in absolute value. It's n. So the probability that the sum of these random variables is greater than epsilon is bounded by the variance of the sum, which is in turn bounded by the expected second moment. This is a Taylor estimate of the distribution by means of the variance. Okay. And then we have Kolmogorov, for which we have also a proof, but I think I will stop here. Kolmogorov. Consider xn independent such that the expectation of xn is 0 for any n. Then, for any a, we have that a squared, the probability that the maximum over k less than n of the absolute value of the sk is being greater than a, is bounded by the variance of the sum. So the difference with Chebyshev is this maximum here. And we should probably review everything up to here again next time. Let's take a break.